Alrighty, welcome back. Hope you enjoyed your spring break. Chapter 9 is taking a look at center of mass and linear momentum. So we're going to start by just looking at center of mass, because that's an important concept in order to understand linear momentum. So if you have a rotating object, it can be pretty complicated. You could imagine flipping a baseball bat through the air, or what I like to do in class at least, is I take a racquetball racket and I fling it across the room. And it doesn't follow a simple shape, but there's a special point where the motion is simple, where it does follow a simple parabolic path, even while the baseball bat itself is flying around, right, at crazy angles. If you followed like the tip of the bat, it would be taking this weird loop path. But the center of mass of the bat traces out that simple parabola just like a ball, just as the same as if I tossed a ball across the room. And all other points on the bat are rotating about this single point. They're spinning around that. So that gives you some conceptual basis for this. So definition now, center of mass, which is often abbreviated as COM, of a system of particles, is the point that moves as though all the system's mass were concentrated at that point and all the external forces are applied there. That's something that's going to be especially important coming back in chapter 12 when we start talking about equilibrium. But these two ideas are key to center of mass. So we could imagine if we have two particles, m1 and m2, they're separated by some distance d. Then if we choose the origin for particle 1, then we could figure out the center of mass of where it is for these two objects with just the amount of mass 2 times d, the distance it is from the other particle, divided by the total mass in the system. And what's shown in the figure is that because the second mass is bigger than the first, the center of mass is not right in the middle. It's not just an average position, it's a weighted average. So it's closer to the heavier particle. Now, this is not our most general equation. We can make it more general if we have an arbitrary choice of origin, right? If we don't assume that m1 is at x equals 0. So if it's at some other position, then we could calculate it with the amount of mass in particle 1 times its position plus the amount of mass in particle 2 times its position. And then once again, divide by the total mass. Because we're trying to get a weighted average of positions, but we don't actually want the masses to be making the position itself bigger. So here's a figure that shows that the x1 position versus the x2 position and x-com defined relative to that same origin as x1 and x2. Now, a neat thing is that in both cases, regardless of how we defined the origin, the center of mass is at the same location. So it's a property just of these particles and not of the coordinate system you use, right? You need to be consistent. You need to choose, okay, if we're going to set x equals 0 at this point, it needs to be that way for all the rest of it. But you can shift the axis and it's not going to change the physical arrangement of these. Now, if we have more than two particles, if we have many particles, we can generalize it for up to n particles, right? And we'll just follow the same pattern. The mass of a particle times its position plus the mass of another times its position, all the way up to the nth particle and dividing by the total mass m, right? Where the total mass is just summing up in the individual masses. And we could write this more compactly using summation notation. So summing up the mass times the position divided by the total mass. This is a really great equation. Anytime you have particles and you want to find the center of mass, you want to be thinking of this equation. Or even if you just have one particle, you want to think of this equation. I guess you'd always have at least two. But there we have it. If we have 2 or 3 dimensions, you can find the center of mass along each one separately. Similar to other cases, we can consider just the x's, just the y's, and just the z's. So more concisely, we could write it in terms of vectors, where the R vector has x, y, and z components all in it. But it's totally fine to work with them individually as well. Now, this is for particles, right? If we have individual masses that are located around. But if we have a solid body, like our baseball bat, or something like a marker, right, which this isn't quite a particle anymore, then we take the limit of an infinite sum of infinitely small particles, right? We could imagine breaking my marker up into little tiny pieces, and we can take that sum, which is going to be integration. So coordinate by coordinate, we could write this equation. I'll tell you right now, in practice, we don't use it of this form very often, but it would be the position times that infinitesimal amount of mass, dm, that we'd integrate over for all the mass of the marker or whatever object, and divide by the total mass, which is just the mass of the object. Now here we're going to limit ourselves to objects that have uniform density, which is much simpler. Because if the object does have uniform density, then the density rho is equal to the infinitesimal amount of mass divided by the infinitesimal amount of volume. But if it's uniform, that's going to be the same density as the overall mass of the object divided by the total volume. So using this relationship, we can instead write our integrals, instead of being in terms of infinitesimal mass, we can write them as volume integrals. And that's what's shown here on the bottom. And this is a much more common way to calculate the integrals here, right? Where you have x, and then you have a volume integral, which you could set up to be, and it might have some x dependence in it, and so then that x makes a difference. So it's 1 divided by the total volume times this integral of each coordinate, x, y, and z, dv. Now, we can avoid taking these integrals if the object has symmetry. So symmetry is something that can really clue us in and give us a lot of help with problems. So here are a few symmetry things to look for. 1, the center of mass is going to lie at a point of symmetry if there is one. So you could imagine a donut, right? A donut has a single point where everywhere else around it, it's symmetric. You could fold it, right, any way, and that would tell you, hey, the center of mass is right at that point in the middle of the donut. And note, I'm going to jump to the third one here. It doesn't need to be on the object. So with a donut, the center of mass is at the hole in the middle of the object. It's not actually part of the object, and that's okay. It's just a location. We also will know that the center of mass is going to lie on a line or plane of symmetry if there is one. So for this example, we could go back to my marker, for instance. The marker doesn't have symmetry top and bottom, right? The top of the marker has this cap, the bottom does not, so that doesn't work. But it does have symmetry on the vertical side, right? Where you could imagine the mirror image on either side is the same. Not worrying about the label too much, right? So that there is this line of symmetry that we could highlight here. So let's try this out with a checkpoint. So I'm going to encourage you, I'll read through this and then I'll encourage you to pause. The figure shows a uniform square plate from which 4 identical squares at the corners will be removed. So where's the center of mass originally? Where's the center of mass after removal of square 1? After the removal of squares 1 and 2? After the removal of squares 1, 2, and 3? After the removal of all 4 squares? So answer in terms of quadrants, which are labeled, axes, or points. This is without calculation. So go ahead and pause and think through each of the answers here. All right, so hopefully you paused. Let's take a look. So for part A, if you originally look at it, the center of mass will be right at the origin, right? Because it's totally symmetric in all directions. So that's the middle where it balances out. If you remove square one, then that's going to suddenly shift your center of mass that there's a little bit more in the fourth quadrant. So you're going to have to shift into this fourth quadrant. Sorry, I don't know why they didn't put the number of the squares following the quadrant number, but this is the fourth quadrant, even though there's a 3 there. And again, because of symmetry, we can even conclude more than just the fourth quadrant. It's going to be along the y equals negative x line, right? This diagonal line here that you could imagine filling in. Actually, I think I can annotate. There we go, right? Because there's equal amounts of mass above and below on either side, so it would follow that line. Now, if we remove squares 1 and 2, right, if these both disappear, then we now have less mass on all of the top very evenly, so it's going to be along the negative y-axis, right? And we could calculate exactly where it is. It'd be somewhere along here, right? Perhaps like there. But at the very least, we know that it is along this negative y-axis. Okay, and then if we remove squares 1, 2, and 3, then it's going to just be, oh, they have an extra one here. Along this line, y is equal to x, but now in the third quadrant. Sorry, I didn't quite draw that symmetrically. And if we remove the fourth one as well, then now it's once again balanced, and so we'd be right back at the origin. So hopefully that gives you a sense of it, how you can look at a situation and use symmetry to get a feel for different scenarios. Oops, and I will clear my annotations. Okay, so one more example and then we'll wrap up. Center of mass of 3 particles. 3 particles of the given masses, 1.2 kilograms, 2.5 kilograms, and 3.4 kilograms, form an equilateral triangle of edge length 140 centimeters. Where is the center of mass of this system? Right, and so for this one, we'd want to think first about trying to draw it. That's especially important here. It mentions it's an equilateral triangle, so all the sides have to have equal length. You'll have to imagine that this is all equal length, right? And we have one at one corner, a slightly bigger one at another point, and the biggest one at another point. Sorry, my labeling is pretty terrible, but I think you can see it. We want to find the center of mass of the system. Note these are particles, so this isn't going to be integrating. This is where we can use our center of mass equation. We can use it in the x and the y direction, right? So for the x direction, we know it's 1 over the total mass times the summation of the masses times their position in x, where I is going to go from 1 up to 3. All right, so if we think about this, right, with the total mass, that's adding these 3 masses up together. So let's see, 1.2 plus 2.5 is 3.7, plus 3.4, that'd be 7.1, I think. And then what we'll want to do is for each of the masses, we want to multiply its position. Now, to determine the position, we're going to need to choose a coordinate system. So I'm going to suggest that we set particle 1 at the origin. This is x and y. And here we're just focused on the x coordinates, right? So for x1, that's just going to be 0. For x2, we can know based upon the edge length that it's exactly 140 centimeters away. So we have that. And then for particle 3, because it's an equilateral triangle, we'll know that it needs to be right in the middle in terms of x. So x3 is going to be half of 140, or 70 centimeters. All right, so that gives us the basis. I'm going to stop trying to write this all out in annotation. So I'm going to clear that and go to the next slide, where we can see the math actually done. So yeah, the total mass was 7.1 kilograms plugging into this equation, and we have mass 1 of 1.2 times position 1, 0, mass 2 times the 140 centimeters, plus mass 3 times that 70 centimeters. And notice it's okay it's in centimeters here, because that just tells us our final answer is in centimeters. And we get something that's slightly past the halfway point at 83 centimeters, which makes sense because mass 2 is bigger than mass 1, so that should shift it over to the right. For the y direction, it'll be much the same, right? Except for in the y direction, both mass 1 and mass 2 are at y equals 0. So they don't go into the calculation for the center of mass of y. It's just going to be the y position of y3, which you can use some geometry or trig to calculate that to 120 centimeters times the value of mass 3, 3.4 kilograms, divided by that same total mass to get the y center of mass of 58 centimeters. So that tells us the coordinates of the center of mass, right? It's at 83, 58 centimeters, which is shown right here in the figure. So not quite the very middle, right? It's closer to particles 2 and 3 because those are more massive than particle 1. All right, so that introduces center of mass. Please feel free to ask questions in the discussion, and I'll see you again soon.